I am Dr. W.B. Gundule from Kamla Nehru Mahavidyalaya, Nagpur. Today we are discussing the what are the types of semiconductors, and as we know, semiconductors have important property. As the temperature increases, the conductivity also increases. This is the important property of semiconductors. And as we know, there are two types of semiconductor, and in case of semiconductors, the conductivity increases, or there is a higher conductivity due to the addition of some impurities, which is known as the doping. Or we can say that conductivity of semiconductor increases by doping. And this addition of small amount of impurities in the semiconductor to increase the conductivity, this process is known as the doping, and the impurities which is added is known as the dopant. And there are two types of we can say that doped semiconductors are two types, where conductivity is higher, and n-type and p-type. N-type of semiconductors are those in which the impurities of the element of group number 15 is added in a semiconductor, and for example phosphorus, like that, and conductivity increases. So there is a higher conductivity, and there is a large number of electrons in conduction band in case of n-type of semiconductor. Whereas in case of p-type semiconductor, we have to add the impurities of element of group number 13 in a pure semiconductor, silicon or germanium. And in that case, the number of electrons are less in conduction band because of the group number 13 elements. So this is known as the p-type semiconductor. So doped semiconductors are two types, n-type and p-type. And also we are discussing in today's part what are the magnetic properties, and as we know, solids have three types of magnetic properties, and one is a diamagnetic, paramagnetic and the ferromagnetic materials. So all these part we are discussing in today's presentation. So today's topic is solid state, and this is the part number 13 of the solid state. And in this part today we are discussing the intrinsic semiconductor and also doping. What are the types of semiconductor, n-type and p-type, magnetic properties, that is paramagnetic, diamagnetic and ferromagnetic solids. So all this part we are discussing in this part number 13. As we know, conductivity of semiconductors can be increased by doping, and the process of addition of small quantity of the impurities to the semiconductor which increases the conductivity is known as the doping. So this is the process by addition of impurity in the semiconductors, and in the conductivity increases, and this process is known as doping. And the impurities which is added is known as the dopant. So what is doping and what is dopant? And doped semiconductors have higher conductivity as compared to the pure intrinsic semiconductor is known as the extrinsic semiconductors. And there are two types of extrinsic semiconductor, and one is a n-type and second is a p-type. So what is n-type and how it is obtained, and p-type how it is obtained, that we are discussing here. So n-type of semiconductors contains large number of electrons in the conduction band, because we are adding the impurity of group number 15, and n-type of semiconductor is obtained by adding the element of group number 15 to the intrinsic semiconductor, and which belong to the group number 14. So element of group number 15 like phosphorus, we are adding as impurity in the semiconductor. So this is known as the n-type of semiconductor. So there is a large number of unpaired electrons in the valence shell of the element of group number 15, and therefore there is a large number of electrons in the conduction band. And n-type of semiconductors is obtained by adding the group number 15 element. And now if we take the example, in case of example, doping of silicon with phosphorus, phosphorus belongs to the group number 15, and silicon has a crystal structure in which silicon atom is linked tetrahedrally to 4 other silicon atoms. Silicon have tetrahedral arrangement and attached to that, and when small quantity of phosphorus as a impurity is added to the silicon, pure silicon, then it occupies the vacant site in the lattice, and therefore phosphorus occupies the lattice site in the lattice, and therefore in place of the silicon, which is also shown in the figure, and with addition of this, the crystal structure remain unchanged, which is shown here in the figure clearly. This is the lattice of the silicon, pure silicon. One of the vacant site is occupied by the phosphorus. So phosphorus have 5 electrons in the valence shell, and out of that 4 electrons are taking part in the bonding with the silicon. So here is bond with the silicon here also, so the bonding. Extra electron is also there. So phosphorus atom occupy the regular site of the silicon atom. So in place of this is the vacant position, and therefore here is a as we know, phosphorus have atom number 15 and electronic configuration is 285. 5 electrons are in the valence shell. So out of 5, 4 electrons taking part in the bonding with the silicon, and 1 extra electrons are here. This is the mobile electron. This is the extra electron of phosphorus, because here, so this is the impurity of phosphorus which is added, and phosphorus atom occupy the regular site of silicon atom in the lattice. So this is known as the n-type of semiconductor. Now what is n-type of semiconductor? Phosphorus is added impurity in the silicon lattice, and phosphorus occupy the lattice site shown in this figure, and there is extra electron. So n-type of semiconductor are those in which the extra electrons are there, or higher number of electrons are there in the conduction band. So extra electron is the mobile electron. So such type of lattice or such type of solid is known as the n-type of semiconductor. So this is about the n-type of semiconductor. So in this n-type of semiconductor, as we have seen, there are 5 electrons. Out of that, 4 electrons are utilized for bonding with the silicon atom, and phosphorus has extra electron. 1 more extra electrons are there which is needed for bonding. Therefore silicon doped with phosphorus has more number of electron in the conduction band. So there are more number of electron in the conduction band as compared to those in a as compared to the pure silicon, which is we have seen in the figure. It is also known that transparent conductivity of silicon that the conductivity of silicon doped with the phosphorus is higher than the pure silicon. Electron in conduction band move under the influence of applied potential, and conductivity increases here. So because of the charge carries a increased number of electrons, silicon or germanium doped with the phosphorus or arsenic or antimony or bismuth is an n-type of semiconductor. So examples of n-type of semiconductor, we have to add the impurity of the group number 15 element. 15 elements are phosphorus, arsenic, antimony, bismuth, forming when we dope with the silicon or germanium, forming the n-type of semiconductor. So these are the examples of the impurity which can be added. So n-type of semiconductors are there, and large number of electrons are in the conduction band. Here is shown also in the figure what is n-type and p-type. So here is a n-type of semiconductor. This is the valence band, this is the conduction band, and here is the extra electron. As we have seen, in case of addition of phosphorus in the silicon, there are the extra electrons are here. So this is conduction band have extra electrons. Whereas in case of p-type of semiconductor, there is a no extra electron here. So conduction band have no extra electron. This is the valence band, and here is a hole. There is a hole because p-type of semiconductor is obtained by addition of element as an impurity of group number 13. For example, boron. Boron have atom number 5, so 3 electrons are there. So less number of electrons are there, which can, so there is a hole. Boron have 3 electrons in the valence shell. Atomic number is 5 of boron. 2 electrons in the first shell and 3 electrons are in the valence shell. So silicon, with the silicon, there is no formation of 4 covalent bond. So 3 electrons utilized for the formation of bonding, and fourth is there is a hole, no bonding, and therefore because of there is a hole, and we can say that there is a less number of electron in the conduction band, or there is no and also there is a hole. So this is the difference between n-type and p-type. Here is the extra electron in the conduction band, no electron in conduction band. Even in valence band there is a hole because there is a less number of electron in the conduction in the valence band. This is about n-type and p-type of semiconductor. Now here, so in case of p-type semiconductor, it is shown that doping of pure semiconductor material like silicon, germanium with the impurity of group number 13 element, we get this type of p-type of semiconductor. This element contains less number of valence electron as compared to the pure semiconductor. For example, if we take the example, pure silicon doped with the boron, then boron atom occupy normal position of the some of the silicon atom in the lattice. But boron atom has only 3 valence electron in the valence shell, and it is not enough electron to form the bond with the silicon neighbors. Boron atom forms band or bond with the 3 silicon atom only, and missing 4th electron create an electron vacancy which is known as the hole. As we have seen, boron have only 3 electrons in the valence shell. It forms the 3 bond with the silicon, but 4th one is a vacant, and therefore this is known as the hole. And here figure shows how p type of semiconductor is there. So this is the boron occupy the normal lattice site in the silicon lattice, and boron have 3 electron in the valence shell, form bond with the silicon. This is bond with the silicon. This, so boron form 3 bond, 1 2 3, but here is a single, here is no, here is a hole. So here is no formation of bonding. So this is no electron, and therefore this is electron silicon, but boron have no electron, therefore this is the hole, no electrons. So there is a less number of electron in the conduction band, as we have seen. So boron atom occupying the regular site of silicon atom, but no sufficient electron to form the bond with the silicon atom, and 1 electron is short, and therefore there is a hole, no electrons, and therefore there is a less number of electron, which is shown here in the figure. So there is a hole, this is the hole, and there is no electron in the conduction band. So large number of electrons are there in the n type, and less number of electrons are there in p type of semiconductor. So this is the figure which shows how boron occupy the normal site in the silicon lattice, and how the p type of semiconductors are there. So there is a difference in n type and p type of semiconductor depending upon the impurity we are adding in the pure semiconductors. Now in case of magnetic properties of the solids, as we have seen, there are different types of magnetic properties. When the substance placed in the magnetic field, they show different magnetic behavior, and magnetic properties of the solid can be understood in terms of classical picture of electrons. In terms of electron, as we know, electron is revolving in a circular orbit, but also it spin around its own axis, and spin of electron produces the some magnetic field, which is known as induced magnetic field. So this is also known as, this electron, spinning electron, is also known as, it behave like a tiny magnet, and therefore produces the field which is known as induced magnetic field. As we have seen, electron is not only revolving around the nucleus, but also spin around its own axis and produces the magnetic field which is known as induced magnetic field. And this field, if orbital contain 1 electron, then the unbalanced spin of exhibit magnetism. So there is an unbalanced spin. When electrons are paired, then the spin is balanced. So here, when electrons, here is if the orbital contain unbalanced electron contain paired electrons, in that case spin is balanced and no magnetic property is observed. On the basis of magnetic properties, solids are now classified into 3 different types: paramagnetic, diamagnetic, and ferromagnetic. So in this case, paramagnetic, diamagnetic, ferromagnetic. So mainly magnetic properties of solids are into 3 types: paramagnetic, diamagnetic, and ferromagnetic. So what are the so these are the 3 different behavior of magnetic properties. So what is paramagnetic material? So we can say that substances which contain unpaired electron. So remember, the substance which contain unpaired electron and weakly attracted by the magnetic field, these substances are called paramagnetic substances. So what is now paramagnetic substances? The substance which contain 1 or more unpaired electrons and are weakly attracted by the magnetic field. Weakly attracted, when the material is placed in the magnetic field, then it attracts toward the magnetic field, weakly attracted. Such substances are known as paramagnetic substances. And spinning unpaired electron give rise to the magnetic moment, and the substance is attracted by the magnetic field of magnetic moment. It is important to understand that such type of substances exhibit magnetism in the presence of external field only. As soon as we remove the field, then there is no any magnetism. When so loose magnetism when the external magnetic field is removed. So when we apply the external magnetic field, then they show this type of behavior. When we remove the magnetic field, then there is no any magnetism of such type of substances. And examples are Cu2 plus, Fe3 plus, chromium 3 plus are some example of paramagnetic substances. So these are the examples of the paramagnetic. Cu2 plus, atomic number is 29. As we know, copper have configuration 3D valential configuration 3d10 4s2. So 2 plus is there. So copper have 4s1 3d10 4s1. So 2 electron is removed from the 4s 1 electron, and from 3d 1 electron. So 1 unpaired electron is there. Similarly, Fe3 plus, chromium 3 plus are some examples of paramagnetic substances. So important point, remember that as soon as we remove the magnetic field, then there is no magnetism. So such type of substances which contain one or more unpaired electron and are weakly attracted toward the magnetic field are known as the paramagnetic substances. Second is there diamagnetic solids, and substance which contain all electrons or paired electron. Such type of solids are known as diamagnetic solids. So substances with paired electrons are weakly repelled by the magnetic field. So there is a repulsion, there is no unpaired electron, all electrons are paired. Such substances are known as diamagnetic solid, and substances are said to be a diamagnetic substances. Because of the pairing of electron, it balances the spin and hence cancel their magnetic moment. And example of such type of solids are nitrogen, fluorine, NaCl, H2O and benzene are some example of diamagnetic substances where all these contain paired electron. So a compound or substance which contain paired electron and are repelled by the magnetic field are known as diamagnetic substances or solid. And as we know, pairing of electron balances the spin and hence cancel their magnetic moment, and because of that they show diamagnetic behavior. So diamagnetic solids have repelled in the presence of magnetic field and contain all electrons are paired. Examples are given here of this type of substances. So these are the diamagnetic solid. And last one is ferromagnetism. This is the property shown by substances which contain large number of unpaired electrons and are attracted strongly toward the magnetic field. And such substances are ferromagnetism. So as we can say that this is the extreme case of paramagnetism. And because paramagnetic contain also unpaired electron, but a large number of unpaired electrons are present in the ferromagnetism. So this is the extreme case of paramagnetism. So substance which contain large number of unpaired electrons are attracted strongly by the magnetic field. Such substances are said to be a ferromagnetic in nature. These substances are permanently magnetized. What is these substances are permanently magnetized. They retain magnetism even after the removal of external magnetic field. If we remove magnetic field also, they show magnetism. So this is the important property of these substances. And example of ferromagnetic substances are iron, cobalt, nickel, gadolinium and chromium oxide. So as we know, iron. So iron is attracted toward the magnetic field even there is no presence of magnetic field. So strongly attracted because contain large number of unpaired electron, and therefore this is the property, third number magnetic property, which is known as ferromagnetism. So there are we can classify magnetic behavior of magnetic properties of the solid into three types: paramagnetic, diamagnetic and ferromagnetic. So this is paramagnetic, diamagnetism and the ferromagnetism. So these are the important three properties of the solids, and their examples also we have seen. So here these are the magnetic behavior, and as we have seen, so there are semiconductor important properties of semiconductor we have seen. An important property of semiconductor, as the temperature increases, conductivity also increases. And also we have seen conductivity of semiconductor can also be increased by the process of doping. So doping means addition of small quantity of impurities which increases the conductivity of the semiconductor. And there are two types of semiconductor that we have seen, n-type and p-type. N-type contain large number of unpaired electron in conduction band, and p-type contain no less number of unpaired electron, and there is no electron in the conduction band. We have seen impurity addition of this impurity of different element in the, and we get n or p type of semiconductors. And there are three magnetic behavior of these solids: paramagnetic, diamagnetic, and ferromagnetic. So their examples also we have seen. So magnetic, in case of magnetic behavior, substance when placed in the magnetic field, they show different behavior like paramagnetism, diamagnetism, and the ferromagnetism. So